Let's summarize what we have seen so far. We have considered a first-order system, so we have considered a state equation of the form x dot equal to ax plus bu, so a first-order linear system, where x, the state, is a scalar quantity. And we have an output equation that is linear again, so of the form cx plus du for some parameters a, b, c, and d that are scalar. And given this system, we found that x of t satisfies the following equation that is given by the variation of constant equation. So, namely x of t at every time t is given by the exponential of a times t times the initial condition x0 plus the convolution integral, that is the integral from 0 till t of the exponential of a that multiplies t minus tau b u of tau in d tau. So this is the formula that we have just found out. So what does this imply for the output y? Remember that for our systems we always want to focus on the input and the output, even though the state is very important too, but if we interpret systems as boxes that are processing a certain input to provide certain output, the output can't be neglected either. So what is the output? By the output equation, we simply have that y of t is given by c times x of t plus du. So we immediately get that y of t is given by c exponential of at times x0 plus the integral from 0 to t. Remember, we are pre-multiplying by c exponential of t minus tau b u of tau in d tau, and let's not forget the term d u of t. So what we have here, the first equation, is called the state solution, and the reason is that it came from solving the solution of the differential equation, and give any arbitrary input u of tau, I can find x at time t, so long as I can solve this integral. And if I cannot, I can always solve it in a numerical way. The second equation instead is called the output solution, because it's a consequence of the state solution to find the output. Okay, and so this is considering first-order systems. We'll see that these formulas actually generalize to the case of higher-order systems. But so far we have seen these formulas in action only for first-order systems. So when x of t is a scalar quantity. What we are going to see now is a concept that is going to be with us for all this class, and it's concept of stability. To be precise, there are many notions of stability. In this class, we'll mostly work with one notion that is called BIBO stability, where BIBO is an acronym and stands for bounded input, bounded output. So, definition: consider a system with initial condition x0 equal to 0. We say that the system is BIBO, and as I said, BIBO stands for bounded input, bounded output, stable if the following relation is verified, if the following condition is met. The condition is that u of t in absolute value is less than u for every time t. If this happens, then necessarily the output is less or equal than y, so here we can have inequality for every t. So let's parse this this relation. What we have here on the left, if this is verified, it means that the input u of t is bounded by capital U at all times. This symbol here is used in logic, in mathematics, a lot, simply implies. So the relation that we need to verify is that if it is true what we have on the left, then the system is BIBO stable if what's on the right is also true. So every time you give me a bounded input, you need to get a bounded output. That's the meaning of BIBO stability. So the relation on the right reads exactly like the relation on the left, but this time it's involving the output. So the output y of t is bounded by capital Y at all times. Okay, this is the definition of BIBO stability. We have specialized it to the specific case of a scalar u and scalar y, but it's not going to be a problem to extend it to the case where the vector u is a vector and y is a vector. In that case, it needs to hold. You need to have every component of the vector to be bounded, but we'll see this. We'll see this later. So far, we are dealing with first-order systems with scalar input, scalar output, and scalar state. And so we're just giving this definition as a preliminary definition for BIBO stability. Now the question is, the question that I might ask is, given what we have seen, is under what conditions a first-order system, is BIBO stable. This is the question that we'd like to ask. So in order to answer this, we just apply the formula that we have seen for y of t. Y of t, we consider its absolute value or its norm, and we try to see under what conditions on the parameters a, b, c, and d, if we give a bounded input, we obtain a bounded output. So the only thing that we need to take is the expression of y of t. Remember that this definition is given assuming a zero initial condition. The reason is that you want to be in a situation where if your input is 0, is exactly 0, then the output is exactly 0 too. And this happens only when the free response is equal to 0. So that's the reason why we are considering initial condition equal to 0. So if the initial condition is equal to 0, then we simply take the convolution integral. And so we take the absolute value of the integral from 0 to t of c exponential of a t minus tau b u of tau in d tau plus d u of t, and we want to find a bound for this quantity when there is a bound for this quantity. So one thing that we can do is we have the absolute value of a sum, so this is less or equal than the sum of the absolute values. So we can immediately write an upper bound in this way. Plus, so you have the convolution integral plus the absolute value of the u of t. And so this is the first step. Then what can we do? We have that the absolute value of an integral is less or equal than the integral of the absolute value. So again, we can write something that is an upper bound in the following way. Absolute value of c exponential of a t minus tau b u of tau in d tau plus, now let's work a bit on this. We take the absolute value of d times, and now u of t, since the input is always, in our definition, we are always considering inputs that are bounded by some value u, we take u of t and we find and we use capital U to upper bound it. Okay, now we mostly have to work on the integral. That's the only thing that is giving us a bit of problems. So in this integral we have that the exponential is always a positive quantity. So we can write this in the following way. Integral between 0 and t, and now we want to write an upper bound for this absolute value. We take the absolute value of c times b times, then we take the absolute value of the exponential, but the exponential is always positive, so we have no problems by removing the absolute value there. The exponential of at minus tau is always positive, times, and then the absolute value of u of tau, for the same reason that we mentioned before, can be upper bounded by capital U. So this is in d tau plus d in absolute value, capital U. And now we are ready for another step. CB and capital U can be placed out of the integral. And now we can simply solve the integral. We are going to solve that in the next step, just to do things in a more ordered way. Plus d capital U. Okay, let's take care of the integral now. CB in absolute value times capital U is the same, and now if we solve the integral we find that this integral is given by this quantity here, and I'll ask you to notice one thing. These steps here are exactly the same steps that we have followed to compute the step response. Actually, this is not a less or equal, this is exactly an equal. So from this previous step to where we are now, the steps are the same steps that we have followed to compute the step response. So if you want to go through them, just verify that they are exactly the same steps. So now the question becomes, under what conditions we have that this quantity is here? The question becomes, under what conditions is on A, B, C, and D, on A, B, C, D, is this quantity bounded for every t. So I don't want this quantity to start becoming too large. So I want to find under what conditions on A, B, C, and D I can find a capital Y such that, doesn't matter what t is, capital Y is always going to be larger than this quantity. So the answer is pretty simple. Let's take a look at this quantity. We grab it here. The quantity here is bounded if, and now we have, is bounded for all t if, for all t greater or equal than 0, of course we are considering only the future of our system, if, and now, well, one simple way to make this quantity bounded is the following. C times B, so either C or B or both are equal to 0. If this is verified, this term with the exponential doesn't give us any problem because it kills the only term that depends on t, and this other term here is just a scalar quantity. So in that case we are definitely fine. Now, the interesting case instead is C times B is different from 0, so both C and B are different from 0, and now we need to check when this quantity here can be bounded by some capital Y. Now, the term D times U doesn't give us any problem. The problem is given by the exponential of AT. This exponential, when A is positive, goes to infinity. So if A is positive, we don't have any bounded stability. If A is negative instead, this exponential, when t is positive and grows, vanishes. So and A is less than 0. The only thing that we haven't considered here is that here I have assumed, when I integrated this, that A was different from 0. The other case is, that I'm going to report here, if A is equal to 0 instead, this quantity is, if you take this integral, is CB capital U UT plus du. So we have the case that we have considered so far is the case A different from 0. And in the case A equal to 0, the quantity CB capital UT is always unbounded for CB that is different from 0. Is this clear? Let's go through this just one time. The question was, when is it true that a linear system of the first order is bounded input, bounded output stable? That means that a bounded input, bounded by capital U, gives me a bounded output, bounded by some capital Y. So what we have done here is just to write Y of t with its expression to start finding some lower bounds, and let's see what these lower bounds look like. We have that definitely with these lower bounds, when A is positive, when A is different from 0, this is our upper bound. When A is equal to 0, this is our upper bound. And we found that for A different from 0, the upper bound is such that the upper bound is unbounded when A is has a real part that is positive, and when instead it is bounded when A is negative. And when A is equal to 0, the quantity that we get here is always going to be unbounded. Okay? So, summarizing, we got that a first order linear system is BIBO stable if A is less than 0, or if C times B is equal to 0, or A is less than 0. This is when a system is bounded input, bounded output stable. Question: have we proven that the system is not BIBO stable for C times B different from 0 and A greater or equal than 0. And I let you think about this question. We are going to answer it as an exercise the other time. So I want you to think though about it. Have we actually proven that this is true? That this is true using this proof or not? What we have definitely proven is that if this quantity is bounded, then y of t is going to be bounded as well. So what I have written here, and I'm going to highlight this in a box, this is absolutely true. That's what we have proven. But the question is, what if this condition is not verified? Is C times B is different from 0 and A is greater or equal than 0? Have we proven that the system is not BIBO stable? And I'll let you think, and we are going to solve this question next time as an exercise.